Everything you have ever touched, tasted, loved, or feared is made of atoms. Everything you can see, the mountains, the oceans, the stars scattered across a clear night sky, the entire visible universe in all its staggering scale, accounts for less than 5% of everything that exists. Let that settle for a moment. 95% of the universe is something we cannot see, cannot touch, and cannot explain. And here is where it gets stranger. We only know it's there because of what it does to the things we can see. It bends light without touching it. It holds galaxies together without being part of them. It shapes the largest structures in the cosmos without leaving a single fingerprint we can read. Scientists call it dark matter. And the more we look for it, the more mysterious it becomes. This is not a story about something distant and academic. This is a story about the hidden architecture of reality itself. The invisible skeleton around which everything, every star, every planet, every atom of every living thing has been arranged. And the most unsettling part? We still have no idea what it actually is. Let's go back to where this mystery began. It is 1933. A Swiss astronomer named Fritz Zwicky is studying the Coma Cluster, a colossal gathering of over 1,000 galaxies bound together by gravity. He measures how fast those galaxies are moving as they orbit the cluster's center. And then he does the math. To move that fast, the cluster would need far more mass than he can see. In fact, based on the visible galaxies alone, the cluster should not exist. The galaxies should have flown apart long ago, scattering into the void like embers from a dying fire. But they haven't. They're still there, perfectly, impossibly bound. Zwicky proposes that there must be invisible matter, dunkle Materie, he calls it in German, dark matter, providing the missing gravitational glue. His colleagues mostly ignore him. The idea is too strange, too uncomfortable. You cannot build a theory on something you cannot see. Then, 40 years later, a quiet and meticulous American astronomer named Vera Rubin changes everything. Rubin is studying the rotation curves of spiral galaxies, measuring how fast stars orbit the center of their galaxy at different distances. In our solar system, the outer planets move slower than the inner ones. Mercury races around the sun. Neptune crawls. This is how gravity works when mass is concentrated at the center. You expect the same behavior in a galaxy. Stars near the bright, dense core should orbit fastest, and stars at the faint outer edges should drift slowly, following the same elegant law. What Rubin finds instead stops her cold. The outer stars of galaxies are orbiting just as fast, sometimes faster, than the inner ones. The rotation curve is flat, not declining. Flat. According to everything we know about gravity, this is impossible. There is an enormous invisible halo of mass surrounding each galaxy, extending far beyond its visible edge, providing the gravitational pull to keep those outer stars moving at impossible speeds. Galaxy after galaxy. The same result every time. The universe is wrapped in something we cannot see. And it is not a small effect. For every 1 kilogram of visible matter in a galaxy, there are roughly 5 to 6 kilograms of dark matter. The stars and gas and dust we see so beautifully in telescope images? They are the decoration. The dark matter is the building. Now, at this point, you might ask a perfectly reasonable question. Maybe we just got the physics wrong. Maybe gravity behaves differently at galactic scales. Maybe dark matter is not a substance at all, just a gap in our equations. Scientists asked exactly that question. They invented an alternative framework, modified Newtonian dynamics, or MOND, that tweaks gravity's rules to explain flat rotation curves without invoking invisible matter. For small galaxies, it works surprisingly well. But then something happened in 2006 that tilted the scales dramatically. Astronomers observed 2 galaxy clusters that had passed through each other in a colossal cosmic collision, an event so vast it makes the entire Milky Way look like a dust particle. This collision is called the Bullet Cluster, and what they saw inside it became one of the most compelling pieces of evidence for dark matter in the history of science. When the 2 clusters collided, the hot gas, the ordinary matter, was slowed by electromagnetic interactions, like 2 crowds of people crashing into each other. But the gravitational mass of each cluster kept right on moving, passing through the collision almost undisturbed, detected only through the way it bent light behind it using a technique called gravitational lensing. The mass was in a different place than the matter. Whatever is providing most of the gravity in those clusters does not interact with ordinary matter. It does not slow down. It does not collide. It passes through as if ordinary matter does not exist. This is not a quirk of our equations. This is a substance with its own rules. Dark matter does not just behave differently from normal matter. It seems to exist in an almost parallel layer of reality, feeling gravity but blind to almost everything else. Think about what that means for a moment. Right now, wherever you are, dark matter is passing through your body, through the walls of your room, through the entire Earth beneath your feet. Trillions of dark matter particles moving through you every second, each one leaving no trace, generating no heat, interacting with not a single atom of your body. You are invisible to them. They are invisible to you. Two universes sharing the same space, forever strangers. The question is, what are those particles? This is where the mystery deepens into something almost philosophical. We do not know. We have leading candidates, carefully constructed theories that fit the data elegantly. But no one has ever directly detected a single dark matter particle. Not once. Not anywhere. For decades, the most popular candidate was something called a WIMP, a weakly interacting massive particle. The name is almost deliberately humble, but the idea is profound. WIMPs would be particles with mass, perhaps 100 times the mass of a proton, that interact with normal matter only through gravity and the weak nuclear force. They would have been produced in enormous quantities in the hot chaos of the early universe, and they would have cooled and spread and clustered into the halos we see today. The beautiful thing about WIMPs is that particle physics independently predicts them. There are candidate particles in theories built for completely unrelated reasons, theories trying to solve problems in quantum mechanics and particle symmetry, that happen to produce exactly the mass and interaction strength dark matter requires. Physicists called this the WIMP miracle. It felt like the universe was handing them the answer. So they built detectors. Extraordinary, ingenious detectors. Deep underground, because you need rock above you to shield out the constant noise of cosmic rays, laboratories were carved out of mountains and mines. In the Black Hills of South Dakota, underneath almost 1.5 miles of rock, sits the LUX Zeppelin detector, a tank containing 10 tons of liquid xenon, cooled to near absolute zero, wired with exquisitely sensitive sensors waiting for the unmistakable flicker of a WIMP bumping into a xenon nucleus. In Italy, beneath the Grand Sasso Massif, another detector listens in the dark. In Canada's Sudbury mine. In deep tunnels bored through the French Alps. Around the world, scientists have created the quietest, most sensitive experiments in human history and pointed them at the void. And heard almost nothing. The WIMP miracle is beginning to look like wishful thinking. Experiment after experiment has ruled out vast swaths of parameter space where WIMPs should have appeared. They are running out of places to hide. Not extinct as a theory, not abandoned, but wounded. The favored candidate for dark matter is losing its grip on certainty. So scientists have turned to other possibilities, each stranger than the last. Axions. These are extraordinarily light particles, so light they exist in a quantum realm almost beyond imagination, billions of times less massive than an electron. Axions were originally proposed to solve a completely separate problem in particle physics, a strange asymmetry in the behavior of quarks, and their properties would make them perfect dark matter candidates. They would be cold, abundant, nearly undetectable. Axion detectors use powerful magnetic fields to try to coax axions into converting into photons, into light, a process so rare and delicate that the detectors must be shielded from sound, from vibration, from almost every form of energy in the environment. They listen for a whisper in a universe full of storms. Then there are primordial black holes. What if dark matter is not a new particle at all, but an old one, a macroscopic one? In the first fractions of a second after the Big Bang, Quantum fluctuations in the density of matter could have produced regions so dense they collapsed directly into black holes before any star was ever born. These ancient, city-sized or mountain-sized black holes would drift invisibly through galaxies, contributing mass without light. The LIGO Gravitational Wave Observatory has detected black hole mergers that have hinted at unexpected mass distributions. Some researchers see shadows of primordial black holes in that data. Others are skeptical. The debate is alive. There is even a class of proposed dark matter called fuzzy dark matter or ultralight dark matter, in which dark matter is a quantum field so diffuse, with individual particles so enormous in their quantum wavelength, that each particle would be larger than an entire solar system. Not a grain, not a clump, a wave, a slow-moving quantum ocean filling the universe with an invisible tide. Each of these candidates is scientifically serious. Each is testable in principle. None has been confirmed. And this is where the story becomes not just about physics, but about what it means to do science in the face of genuine mystery. For a century, physics has proceeded by prediction and confirmation. Einstein predicts gravitational waves. 100 years later, LIGO detects them. Theorists predict the Higgs boson. The Large Hadron Collider finds it. The model works. The prediction is rewarded. Science accelerates. But dark matter refuses this rhythm. It predicts its own existence through irrefutable gravitational evidence, and then it hides. Every instrument we aim at it comes back almost empty. This is not a failure of science. It is science functioning at its absolute frontier, mapping the edge of the known against the vast interior of the unknown. There is something else worth understanding about dark matter. Something that gives the mystery a different dimension entirely. Dark matter did not just sit passively in the background while the universe formed. It was the architect. In the early universe, hundreds of millions of years before the first stars ignited, dark matter was already clumping under its own gravity, forming invisible halos. And those halos became the scaffolding of the universe. Ordinary matter, flowing through the cosmos like a slow gas, was pulled by gravity into the wells carved by dark matter. Gas fell into dark matter halos and condensed. It was heated. It ignited. The first stars were born inside structures of dark matter we will never directly see. The largest telescopes we have built confirm this. The cosmic web, the enormous filaments of galaxy clusters connected across hundreds of millions of light years, separated by vast cosmic voids, traces almost perfectly the expected distribution of dark matter as modeled by supercomputer simulations. When we run those simulations, feeding them only the rules of gravity and the initial conditions of the early universe, the dark matter organizes itself into exactly the structures we observe today. The cosmic web we see in light is the echo of a scaffolding built in darkness. Without dark matter, there would be no galaxies. Without galaxies, there would be no stars. Without stars, there would be no planets. Without planets, there would be no you sitting here, wondering what the universe is made of. The invisible thing made every visible thing. Now we approach the deepest layer of this mystery. And it is not comfortable. It is possible that dark matter is not a particle at all in any sense we currently understand. It may be something fundamentally outside the standard model of particle physics, the framework that describes every known particle and force with extraordinary precision. The standard model is one of the most tested and successful theories in the history of science. And it does not predict dark matter at all. The neutrino, the ghost particle that passes through matter almost as freely as dark matter, was once unknown too. It was proposed by Wolfgang Pauli in 1930 because energy seemed to be disappearing in radioactive decays, and he needed something invisible to carry it away. It took 26 years to detect the first neutrino. Pauli wrote in a letter that he had done a terrible thing. He had postulated a particle that could never be detected. He was wrong. The neutrino was found. Dark matter may be our generation's neutrino, a particle so strange, so weakly connected to our instruments, that we have simply not yet built the right detector, the right approach, the right question, or it may be something no theorist has yet imagined, a force that operates on a hidden sector of reality, populated by particles that interact among themselves but share with us only the pull of gravity. A shadow universe, complete with its own physics, running alongside ours, separated not by distance but by the walls of interaction. Two worlds sharing one space-time, each invisible to the other. It is worth pausing here, because this is not science fiction. These are peer-reviewed proposals, taken seriously by serious people, because the evidence demands seriousness. When 95% of the universe is unknown, the hypothesis space must be vast. There is one final layer to this story that rarely gets discussed. And it may be the strangest of all. We have been talking about dark matter as something separate from us, out there, in halos around galaxies, in filaments between galaxy clusters. But the Milky Way has its own dark matter halo. And we are inside it. The solar system orbits through a sea of dark matter, denser toward the galactic center, thinner at the edges. Earth passes through this sea at hundreds of kilometers per second. And some researchers have proposed that this local dark matter density might not be irrelevant to us. Not to human civilization, not to technology, but to life itself. There are serious, careful papers exploring whether dark matter, accumulated inside the Earth over billions of years, might contribute to geological heating in ways too subtle to measure currently. Whether periodic changes in the solar system's orbit through regions of different dark matter density, crossing the galactic plane every 30 million years or so, might correlate with disruptions in the inner solar system. Disturbances in cometary paths. Extinction pulses. The data is too weak to conclude anything, but the possibility is genuine enough to investigate. The invisible architecture of the cosmos may have left fingerprints in the history of life on Earth. Dark matter is not just a cosmological curiosity. It may be woven into the story of every species that has ever evolved, and everyone that never got the chance. We are left, then, at the edge. The universe is mostly made of things we do not understand. Dark matter, the dominant material by mass in galaxies, the architect of cosmic structure, the invisible ocean in which all visible matter swims, remains, after nearly a century of investigation, unidentified. We know with extraordinary confidence that it exists. We know how it behaves gravitationally. We know what it was built. We know what it is not. We do not know what it is. And there is a strange beauty in that. Not a comfortable beauty, a demanding one. The kind that refuses to let you look away. Every image from the James Webb Space Telescope, every galaxy gleaming in infrared light against the black of deep space, is showing us something built on a foundation we cannot see. The light we capture is the surface. The reality beneath it is dark. The next decade may bring resolution. The LUX Zeppelin detector is pushing into sensitivity levels that should either catch WIMPs or rule them out definitively. Axion experiments are reaching the precision needed to probe serious theoretical predictions. The Vera Rubin Observatory, named for the woman whose observations made dark matter undeniable, will map the southern sky with unprecedented depth, cataloging the shapes of hundreds of millions of galaxies and using the subtle distortions of dark matter's gravitational lensing to map the invisible scaffolding in extraordinary detail. The Euclid Space Telescope is already doing the same from orbit. We are closer than we have ever been. And we are still in the dark. That is the honest answer. After a century of searching, after detectors buried under mountains, after supercomputer simulations of billions of galaxies, after gravitational lensing maps of the largest structures in the universe, after dozens of theorists spending entire careers on the problem, we are closer, and we are still in the dark. But consider what that means for a moment. Every prior era of science that confronted a great unknown eventually broke through. The atom seemed metaphysical until we split one. The expansion of the universe seemed like a reckless hypothesis until the light of a billion galaxies confirmed it. The gravitational waves Einstein predicted seemed too small to ever measure, until the most sensitive instrument ever built felt the tremor of two black holes colliding a billion light-years away. Science does not defeat mysteries quickly. It defeats them inevitably. When dark matter finally yields, and it will yield, it will not just fill a blank in a textbook. It will open a door. Because if dark matter is a particle, that particle fits into a larger theory of physics that extends beyond everything we currently know. And that extension may explain things we have not yet thought to ask. It may reveal forces we did not know existed, particles we never suspected, perhaps the beginnings of an understanding of why the universe has the specific laws it has, why the constants of nature are what they are, why anything exists at all rather than nothing. Dark matter is not the answer to one question. It is the key to a larger room. We live on a pale blue speck orbiting one ordinary star among 400 billion in one ordinary galaxy among 2 trillion in the observable universe. And around all of it, wrapped invisibly around every galaxy, woven through every filament, threading the vast and silent spaces between all the lights we have ever seen, is something we cannot name. Something that outweighs everything we can see by a factor of 6 to 1. Something that built the universe and still holds it together, in silence, without asking to be understood. It is there, right now, passing through you, through this planet, through the sun itself, leaving no mark, seeking nothing, bending space-time as it goes. The universe's greatest secret is not hidden in some remote corner of deep space. It is everywhere. And we are only just beginning to learn how to listen for it.